Okay, in this section, we want to explore how to calculate greatest common divisors using the Euclidean algorithm. And so that starts with the division algorithm.
So this is our method of long division. If I have a couple whole numbers, I want to divide them. So I'm doing A divided by B. And I want to see how many times does B go into it, and then we'll come up with a quotient here, and we'll get a remainder down here. So what we're saying is that if I want to do A divided by B, there exist unique integers Q and R such that the dividend A is Q times B plus R, where the remainder R is smaller than the divisor B. Now, B can be negative, so I need to put absolute values here. So Q, the number on top, is called the quotient. That's the multiplier on the divisor B, and R is the remainder. Okay, let's just prove the case where B is positive. So I'll draw a number line. Here's B, and here's our bigger number A. We'll have 2B, 3B. You keep going until we get the biggest multiple of B smaller than A. And we know such a multiple exists because the set of such multiples is bounded above, and so you have some maximum element principles telling us that there will be a maximal multiple of B smaller than A. And then the next one, Q plus 1B, is strictly bigger than A. So I'm going to define Q to be such that QB is the largest multiple of B less than or equal to A. So then we would have QB is less than or equal to A. That would be strictly less than Q plus 1B, because that's a larger multiple of B. So how do I want to define the remainder R? Well, the remainder R is just this little difference right here. So we'll define R to equal A minus QB. Well, isn't that convenient? Because that would immediately imply that A equals QB plus R. Okay, so that gives us the first part, and then we want to show the remainder is smaller than B. So come back to this inequality right here and just subtract QB. And star, and then we'll get QB minus QB less than or equal to A minus QB, strictly less than QB plus B minus QB. So I subtract it from all sides, and that gives us exactly what we want. We have 0, less than or equal. This is the remainder R, and we have B right here, which is our second condition when B is positive. Okay, you can think about how to modify that for a negative B. Let's go on to the uniqueness part now. Okay, in the uniqueness part, we suppose I've got two different quotients and remainders, a Q1B plus R1 and Q2B plus R2 for some integers Q1, Q2, R1, R2, and Z, with the remainders strictly less than B and non-negative. Okay, then focus on this equality. So I'll just subtract the QB's over, and I'll get Q1B minus Q2B is R2 minus R1. Factor out the B. So the left-hand side is a multiple of B, and how big is the right-hand side? Well, these two numbers are strictly less than B. So the furthest apart they could possibly be is B minus 1. So let's just take absolute values of everything here. B is positive, so that's doesn't need any absolute value. And so the left-hand side is a multiple of B, and the right-hand side is strictly less than B, because R1 and R2 are trapped in this interval. Well, what does that mean? You have a multiple of B strictly less than B, or you could go ahead and just divide out the B. You have some integer here. That's an integer whose absolute value is less than 1. Well, there is only one integer satisfying that. That would mean Q1 minus Q2 is 0. So Q1 equals Q2. And then returning to our starting point right up here, R1 equals R2. And that gives us the uniqueness. Okay, now there's a modified division algorithm. I'll call it the minimal remainder division algorithm, where you allow the remainder to be positive or negative. And by doing that, we can make the absolute value not only less than B, but less than B over 2. So what is the idea here? On that same picture, and for convenience, I've gone ahead and stated it with B being positive. So here's the QB, and here's Q plus 1B. And notice Q plus 1B is a little closer to A than QB is. So I would rather use this as a remainder, because that in absolute value would be smaller than the traditional remainder. So that's our standard remainder here. So we start the proof by just employing the standard division algorithm. By division algorithm, A equals Q1B plus R1 for some Q1 R1 with 0 less than or equal to R1, strictly less than B. Okay, now if the remainder R1 happens to be smaller than B over 2, we're done. So if R1 is less than or equal to B over 2, we take Q to be Q1 and R to be R1, and we're done. So it's exactly the same as the standard algorithm. If, on the other hand, this remainder, this is the R1 value right here, let's call it R1 right there, is bigger than B over 2, then this one is going to be the smaller one. So then we take Q to be the next multiple of B, So let it be Q1 plus 1. And R would be Q1 plus 1B. It would be A minus this one right here. So I can't put that in here. A minus Q1 plus 1B. Okay, then the claim is that this value of R does the trick. So once again, we would have R is A minus QB. So A is QB plus R. So that works again. And how big is R going to be? So A minus Q1B is, just a minute. Okay, so coming back to this equation right here, so we have A is Q1B plus R1. R1 is bigger than B over 2. So by the definition of R1, that means that A minus Q1B is strictly bigger than B over 2. And then we subtract B from all sides. That A minus Q1B minus B would be greater, strictly greater, than minus B over 2. And this is R. So R is strictly bigger than minus B over 2, and clearly R is a negative quantity. So we have that minus B over 2 is less than R, is less than or equal to 0. And so in absolute value, it is bounded by B over 2. Okay, so we've got this one. So for comparison, let's just do an example. If I'm doing 29 divided by 5, then using the ordinary division algorithm, we would have 5 times 5 plus 4. So here's 29, and the biggest multiple of 5 smaller than it is 25. The next multiple of 5 is right here. So the ordinary algorithm has a remainder of 4. But if we want a minimal remainder, I would take 6 times 5 and then subtract 1. That come out to 30. Okay, now let's do the Euclidean algorithm. So this is the procedure for calculating GCDs. And the standard Euclidean algorithm just means use the standard remainder when we do the division algorithm. So suppose I want to calculate the GCD of A and B. Then I'll say, oh, A is some multiple of B plus a remainder R1. And then calculating the GCD, we would say AB is equal to A minus Q1B, comma B. So we use the subtraction principle or the invariance principle we did on the last lecture. This is the remainder R1 right here. So the GCD of A and B is the same thing as the GCD of R1 and B. And now, B is the larger of the two numbers, so I repeat the division algorithm by subtracting a multiple of R1 from B. So I'll say B is R1 Q2 plus some R2, where the remainder R2 is strictly less than R1. And then I'll subtract that multiple of B from R1, leaving me with a remainder of R2. So I replace B with B minus R1Q2 to give me the R2 in its place. And so now we're down to smaller numbers yet. And so at each stage we get smaller and smaller numbers. So I take now the bigger of the two numbers, R1, divide it by R2, leaving me with a remainder of R3. And you keep going. And since these numbers are strictly decreasing, eventually we get to a point where the remainder is going to be 0. Because a strictly decreasing sequence of positive integers has to terminate in a finite number of steps. Okay, so at this step right here, this is our kth step, we have k minus 2 remainder is rk minus 1 times some qk. And the previous step, you've got an rk minus 1 sitting right there. Okay, so the GCD then is just the k minus 1 remainder, right there. So we're guaranteed the process will stop in a finite number of steps because it's a strictly decreasing sequence. Okay, let's do an example. Suppose I want to find the GCD of 126 and 49. So I take 126, I divide it by 49, it goes into there twice. That's 98 with the remainder of 28. So at this point, I'll subtract 2 49s from 126 to give me the remainder of 28. Now 49 is the bigger of the two numbers, so I divide 49 by 28. It goes into there one time with a remainder of 21. 28 is now the larger number. 21 goes into that one time with a remainder of 7. 21 is the big number. And 7 goes into it 3 times with a 0 remainder. Okay, so we are ready to terminate the process, and the GCD of 7 and 0 is just 7. And again, it's sitting right there. So let's look at the running time for the standard Euclidean algorithm. So you can show it, and these are things I'm just going to point out to you. I'm not going to prove these facts, that the running time is slowest for calculating the GCDs of consecutive Fibonacci numbers. Now we'll be talking about the Fibonacci sequence in detail later in the semester, but just as a reminder, it's the sequence where you obtain each successive term by adding the previous two terms. So suppose you wanted to calculate the GCD of 13 and 21. Those are consecutive Fibonacci numbers. Notice every time you divide, the quotient is 1. 13 will go into 21 one time, leaving you with a remainder of 8. 8 goes into 13 once, with a remainder of 5. 5 goes into 8 once. So you're going as slow as possible because the quotient is always 1. 3 goes into 5 twice. 2 goes into 3 once. 1 goes into there. And bingo. And of course, it turns out that the GCD of any two consecutive Fibonacci numbers is always going to be 1, as this process is indicating. Now, the Fibonacci sequence is essentially a geometric sequence, geometric growth. They are very close to 1 over the square root of 5 times phi to the n power. So the nth Fibonacci number is very accurate approximation, where phi is the golden ratio, 1.618 dot, dot, dot. So it would follow that the number of steps in this process, so this requires n minus 1 steps to calculate this, starting with Fn, which is our bigger number. And so if Fn is this value, what does that mean? Take the log to the base phi of both sides. So you're saying root 5 Fn is roughly phi to the n. And so log to the base phi of root 5 Fn is approximately n, the number of steps. And then subtracting 1 from both sides, we get that n minus 1, which is the number of steps, is approximately this value. And you can show, in fact, that the number of steps is at most log to the base phi of Fn. And that's the worst case scenario. So the number of steps for calculating the GCD of any two numbers using the standard Euclidean algorithm is on the order of log to the base phi of b. In the fast Euclidean algorithm, we do the same thing, but at each step, instead of taking the positive remainder, we'll take the smallest remainder. So we want the absolute value of r to be bounded by half of the previous remainder. And so you're knocking the remainders down by a factor of 2 at every step. So the first remainder is smaller than b over 2, the second one is smaller than b over 4, and the jth remainder is smaller than b over 2 to the j. So the algorithm will stop as soon as the remainders get smaller than 1, which means as soon as 2 to the j is bigger than b, the algorithm terminates. So this time the number of steps is on the order base b of a, which is better than log to the base phi. So you're saving time doing the fast Euclidean algorithm.